In our penultimate video here, we're going to talk about two more types of reactions, the Aldol condensation and the Calisen condensation. So first off, the Aldol, as the name kind of implies here, it is the sort of mixture of an aldehyde and alcohol. So to sort of orchestrate this reaction, we need to react essentially two aldehydes together. For a lot of these videos, we've been looking at carbonyls reacting with electrophiles, but we can also have this sort of self-condensation happen, okay? And so to do this, we can actually use a weaker base here. The pKa of aldehydes is about 17, so it's almost like water, right? So it's actually fairly acidic compared to simple ketones. So we use some sort of base followed by an acid. And so what we end up seeing here is the formation of this species here, right, where we have our two components sort of combined together, right, making a new carbon-carbon bond. So we have a nucleophilic aldehyde and an electrophilic aldehyde to do this addition reaction. So they're combining together and we're not reforming the carbonyl. So what does the mechanism for this look like? So we have an aldehyde here, right, and we have our carbon at the end, right, with all our hydrogens, and we can treat this with NaOH, right, and we are using a weaker base than we've been before, because we can do that with aldehydes, right, because that pKa is lower, and to sort of prevent any side products from happening, we can use a weaker base, right, which ends up abstracting one of these hydrogens to get to our enolate here, which will act as the nucleophile for our aldehyde, right? So one aldehyde is nucleophilic and the other is electrophilic. And we get to our intermediate here, right, which then, right, we add our acid in the last step to get to our aldol. Right, and notice, right, we've made a new bond between, right, our nucleophilic carbon and the electrophilic carbon, right, which is this new bond here. And then the aldehyde, right, that hydrogen that was there, right, is still here, right, because we reformed the aldehyde, right, and then we react the other side. Right, so all our carbons are still present. We've just made, right, a new species out of it. And so underneath, right, if we force this reaction further, so by forcing addition, we just mean heat, right, which is kind of a way of saying energy, where we're adding more energy to a system, we can do something like this, where we can take an aldehyde, right, two equivalents of an aldehyde, right, and with sodium hydroxide and adding heat at the end, we can see this situation occur where, right, we have one aldehyde, and at the bottom, right, we have our OH here. What'll happen is the hydrogen that's present here will end up getting abstracted by the O-, and you can actually remove the OH here in a elimination reaction, right? Because we know OH can be, you know, a decent leaving group, right? So this only occurs again under heat, right, to make this last step happen. And so now, instead of having an alcohol at the end, right, still an aldol condensation, we're just taking it a step further, we generate this alkene here, okay? And this is known as a alpha beta unsaturated aldehyde. And that terminology comes from the alpha and beta carbons here, right? It just means there's an alkene, right, this unsaturation present that is in the alpha beta position next to the right next to the aldehyde. And we can do the same sort of thing with ketones, actually. The only difference here is that ketones are less reactive than aldehydes. So they only work in this particular case with this intramolecular reaction. So I'll leave this up to you to do. Remember, this is forcing conditions, and we can take a look at this in class. Okay, same sort of principle. We're just going about it in a slightly different way here. And we'll take a look at some more of these reactions in class as well, okay? So the next set of reactions we're going to look at is this. We're going to start here with the Calisen ester condensation. So we are using, come on, we're using esters instead of aldehydes, right? So this is essentially the aldol with esters, okay? And moreover, this is going to be substitution, so we're reforming carbonyls all the way through and not addition. Okay, and one other piece I want to point out here is when we're using our bases here, we want to use a base identical to the ester. And I'll explain that a little bit more in detail. So we have, for example, two esters here, right? And over our reaction area, we have a base, right? Notice we have our ethoxide here, similar to the ethyl group coming off our ester. And then acid to quench the reaction when we're done, and we get the following, where it looks like we've lost, right, the ester component on one of our esters here, and made this diketone or dicarbonyl species. So the mechanism for this looks as follows, where we have our strong base here removing one of our hydrogens to get to our enolate, which now, again, just like the aldol, will act as the nucleophile, and it will attack our other ester species. To kick it open, or kick that carbonyl open, and make this connective species here. Right, and notice the nucleophilic carbon and the electrophilic carbon, right, has made this new bond here, okay? And then, right, our electrons coming back down, right, we can kick off this ethoxide here as our leaving group, and this is where that substitution comes into play. Right, so I'm flipping this right side up again. And we have still, right, this new bond that was formed is here, right? And we've removed that that ethoxide group, which is here. And right, it does get quenched during the course of the reaction, right? So the O- will eventually become, right, ethanol. Notice, right, there's no alpha, beta unsaturation occurring, right? We're not forming that ketone there because we already have a leaving group that is left, right? We can't really do that again like we saw with the aldol, where we can remove the OH. Here, right, we're just kind of stuck at the carbonyl site, right? And we can look at something a little similar called the Dieckmann condensation, which is essentially just an intramolecular Calisen. Just some old white dude named Dieckmann decided to name a reaction after himself, but it's really just an intramolecular Calisen reaction. So what I'm going to do here is I'm going to draw out all the components for us. And we can use, we don't have to use that ethoxide. We can also use some traditional methods here with NaH, right? And this allows us to get to this species here, right? This Calisen, but we're just doing intramolecularly, right? There's this tether attaching, right? This 4-carbon tether attaching our groups together here. So we want to be sort of wary of that while we're doing this reaction, right? So we can look at this mechanism in class as well, okay?